Today we're exploring Stokes' theorem. It connects what happens on a surface to what happens along its edge. Before we go into 3D, let's build some intuition in 2D. Let's imagine ourselves a closed curve C drawn on a flat surface S. Now, Green's theorem tells us that the circulation of a vector field around that boundary curve is equal to the sum of the curl across the entire region inside. Now, if we lift that idea into 3D, instead of a flat region, we now have a curved surface S floating in space. Think of it like a curved soap film. Its boundary, the curve C, wraps around that edge. Stokes' theorem says that whatever is happening across this entire surface is encoded in that single boundary curve. Now, here's a vector field. We have arrows showing the direction and strength of some force at each point in space. When a field swirls or rotates locally, we call that the curl. Stokes' theorem tells us that adding up all that curl across the surface equals the total circulation of the field once you travel across the boundary. And here I'm showing it formally. The line integral on the left measures the circulation across C. The surface integral on the right measures the total curl through S. They are always equal. That's the theorem of Stokes. Let's verify this with an example. We'll use a simple vector field f is equal to negative y x 0. Our surface S will be a flat unit disk sitting in the xy plane bounded by the unit circle C. We are going to prove that the surfaces swirl and the boundaries we walk give us the exact same value. First, the surface. We calculate the curl of f. Using the determinant of our partial derivatives, the I and j terms vanish. The k component gives us 1 minus negative 1, which equals 2. So our curl is a constant vector 2k, pointing straight up. Since the disk is flat, the normal vector ds is just k dA. Multiplying our curl by the area of the disk, which is pi, gives us a total of 2 pi. Now for the boundary. We parameterize the circle as cosine t, sine t, 0. When we take the dot product of our field f with the velocity vector dr, it simplifies down to sine squared t plus cosine squared t, which is exactly 1. Integrating 1 from 0 to 2 pi gives us, once again, 2 pi. Both sides equal 2 pi, so our theorem holds. In Stokes' theorem, if a surface integral is too complex to solve, you can always just do the other side.